Because you have to click on the.
Ready to go?
Yeah.
Okay, it's a pleasure to introduce the final speaker of the morning to continue this course. It's Davide Ravotti. We'll talk about ergodic and mixing properties of Horocycle flows and their time units.
Thank you very much. Thank you everyone for coming. So we'll start by, we need to finish some material from the previous lecture, but I'll start from a quick summary of what we did last time. So what we did was studying the group G, SL2R, so 2 by 2 matrices with real entries and determinant 1. And what we did was, so we want to look at some nice smooth flows on portions of this group. So first of all, we consider any discrete subgroup gamma, and we were looking at quotients, and I like to take left quotients that I call M. And we observed that so G is the structure of a smooth manifold inherited by R to the 4, and if gamma is a discrete subgroup, then this quotient also has a structure of smooth manifold. So this is a very nice space to. So yeah, it's a very good space to look at and try to do dynamics. And what were the flows that we were interested in? Well, so the construction was the following. So we first look at the tangent space at the identity, and we identified as the linear subspace of all 2 by 2 matrices with 0 trace. And we noticed that every time we fix any element in this tangent space at the identity, actually we can define a smooth vector field on all G and on all M, because this vector field is going to be left invariant, so it will be well defined in the quotient as well. So it's a smooth vector field. We can try to integrate it, and indeed this gives rise to a smooth flow on this space. And explicitly, this smooth flow is given by multiplication on the right by the exponential of t times the initial matrix that we started with. So it's and these are called homogeneous flows. So there are two descriptions. So if you like, you can think of them as on quotients of your group. They are given by multiplication on the right by exponential of t times some fixed matrix. Or if you like a more geometric description, they are obtained by integrating a left invariant vector field. So a vector field coming from a specific choice of a tangent vector at the identity. So this is these are our flows, this is our space. We also introduced a measure that is called the Haar measure. And we define it explicitly, but what we need for the rest of the course is just that it's a smooth measure that is preserved by any flow of this type. And I want to point out maybe just a quick remark. So if instead of, so we were looking at the group SL2R, right? But you can try to do the same construction if you take, for example, R2, and if you take gamma to be Z2, then now my space M would be the torus, T2. So what is, so here I'm looking at tangent space at the identity being 0, so the tangent space as 0 in R2 is R2 itself. So my boldface W would be just any element of R2, and maybe you take in non-zero. And what is this flow that we obtain? Well, it's obtained by the group operation of the, so here it's the, in this language, you should think of this exponential as the exponential in Riemannian geometry, not the exponential in, not the, in real analysis, but in Riemannian geometry. So this flow, so the vector field generated by this flow is the constant vector field with the same slope. So this flow in WT in T2 is just the flow that takes a point X and maps it to X plus TW. So these are the linear flow that John was defining. So what we are doing here is really, so if this is my space E2, this is my tangent space at the origin, which is R2. So here I'm choosing a vector W. I'm defining the constant vector field. The last time I defined by capital W. And the flow phi t is the straight line linear flow that John is talking about. So what we are doing here is really, if you want the direct analog of these straight line flows in a non-abelian. So just to put it in perspective. So this was just a comment on the side to motivate, if you want, also the study of this type of flows. We introduced two objects that, so we introduced the adjoint, which was given by conjugation by an element of the group, and we described its dynamical interpretation being the differential of the time t map of this flow. So this is telling you how the dynamics acts on tangent vectors. And the little adjoint, which was obtained by the bracket operation with W, and the dynamical interpretation is the Lie derivative with respect to the vector field W. So this is telling you how the dynamic acts infinitesimally on tangent vectors. So this is the derivative at p equals 0, this with the minus sign in here. And so with this operation, this the tangent space of the identity turns to be an algebra that is called the Lie algebra of the group. And now we will finish by introducing this operator. So let me go back. Okay, so we introduced last time the killing form, which I just recall. It was defined, it was a bilinear form defined in this way. And what we observed is that in this basis, Rx, Y, maybe I'll just write it down in case forget. So R was the matrix 0, -1, 1, 0. X was the matrix 1/2, 0, 0, -1/2. Sorry for, and Y was the matrix 0, 1/2. I don't know, maybe here I took a 1/2 as well, actually. Yes, I also took a 1/2, sorry. 1/2, 0. Okay, so with respect to this basis, we computed what this killing form is, and we found out it was with respect to this basis, it's in a nice diagonal form. In particular, it's of signature of 1, 2, and it's non-degenerate. And we also observed that this helped us to define an action of G and of the quotient G modulo plus minus the identity PSL2 on the hyperbolic plane that also Reynolds was talking about, although in a different model of the hyperbolic plane, but it's the same action. So now I want to define an object that would be very important also for what we are going to talk about today, that is called the Casimir operator. So, okay, so as I remind you, the killing form that we define is non-degenerate. So every time we have a non-degenerate bilinear form and we have a basis, we can look at the dual basis. And because with respect to this basis, my matrix was in a diagonal form, the dual element of R is -R, the dual of X is X itself, and the dual of Y is Y itself. Okay, because it was -1, 1, 1. And also, as I also reminded you before, every time you have an elements in the Lie algebra, they can be identified with vector fields. And also last time I mentioned that vector fields, I will interpret them as derivations. So when I write vector field applied to a C1 function, I mean the derivative of that function in the direction of that vector. Okay, with these facts in mind, I can define the Casimir operator. So the Casimir operator is a second order differential operator. So what am I doing? I fix the basis and I've taken the dual basis, and then I define the Casimir operator as the sum of each element of the dual basis composed with its own dual. Okay, so would be R times minus R. Here I'm taking a minus sign. So this would be minus, then an element composed with an element of the dual basis. So R minus R with a minus becomes R squared. X composed with X, it's X squared, and I put a minus in front. And Y composed with Y, it's Y squared with a minus in front. And this is called the Casimir operator. So it's so these elements are derivatives, and I'm doing them twice. So it's a second order differential operator. It's a sum of partial derivatives of second order. And I want to mention some properties. So the first property that we need to observe to make sure that this is a good definition is that the definition of the Casimir operator, well, I fix the basis and I define with the Casimir operator, but actually the definition is independent of the choice of the basis. So it's a good object to look at. A very important property is that it commutes with all vector fields, all left invariant vector fields, all vector fields coming from elements of the Lie algebra that you can take. And another property that maybe connects this Casimir operator that was defined algebraically to some geometric object is that, so remember that SL2R was acting on the hyperbolic plane by isometries, and we also found that the stabilizer of one point was the group of rotation, SU2. This also appeared in Reynolds' lecture, so that we could actually identify the hyperbolic plane with the quotient of the group modulo the rotation subgroup. And so I can define, since by this identification, if I now take a C2 function on the hyperbolic plane, I can think of it as a C2 function on G that is invariant by rotations. So I can think of functions on the hyperbolic plane as, again, functions on G invariant by SO2. And the rotation is generated by this element here. So I can think of them as function on the group such that the derivative in the direction of this vector field is 0. And it turns out that this operator, the Casimir operator on functions on this type, coincides with the hyperbolic Laplacian, minus the hyperbolic Laplacian. Let me sketch at least a proof of this proposition. So the first point basically is a consequence of the definition. So recall that, okay, I have to show it's independent of the basis. So let us fix two bases, one Wi's and one Zi, and the dual basis. And now the proof is just you have to remember from linear algebra. So if you have a matrix that tells you how the basis change, from a matrix that tells you the change of basis from this one to this one, then the corresponding change of basis in the dual space is given by the inverse transpose. So that if the change of basis is given by some matrix Aij, then the matrix given by the change of basis, but in the opposite direction, is the transpose. So that when you multiply an element times its dual, you have a matrix times its inverse transpose, and they cancel out. This is a computation. And we want to prove that it commutes with all vector fields. So I have to show that every time I do Casimir compose a derivation, then it's equal to the derivation composed with the Casimir. And you can do it in full generality. There is a general argument that works not just for SL2, but for any semi-simple group. But in our case, you can do it by hand. You can compute explicitly. You can verify it for any element of the basis. Once you done it for elements of the basis, it will also for any linear combination of these guys. And then it's a case-by-case computation, if you like, and you can do it explicitly. So if you write it out, then you want to commute R, for in this case, you want to commute R with X, R with Y. And, so here, I didn't write the term in R because here there was a term in R squared, but they cancel out immediately because it's just R3 minus R3. And the other ones, you just want to commute the operator, but every time you commute, you have to introduce the commutator because they do not commute in general. and you write it out, expand, and see that you actually get 0. And to prove that it coincides with the hyperbolic Laplacian, well, this is a fact from hyperbolic geometry that the metric on the hyperboloid model of the hyperbolic plane comes from the restriction of the Killing form on the hyperboloid. And you can check that the vector fields x and y are orthonormal with respect to this metric, so that the hyperbolic Laplacian, being the divergence of the gradient, is precisely x squared plus y squared. So this the second derivative. So recall that the Casimir was r squared minus x squared minus y squared. So on functions that are invariant by r, you're left with minus x squared minus y squared. Okay, so this is all for the preliminaries, and now we can start our investigation of Horocycle. So if there are questions, this is an excellent moment for Thank you. So today we want to study the Horocycle flow. So what is the Horocycle flow? The Horocycle flow is the flow defined as we did in general for homogeneous flows, where, so this is the Horocycle flow, where the element u is this one. So sorry, I don't know if you can see, is the matrix 0, 1, 0, 0. So what we want to do is study, I'm sorry for this. We want to study its ergodic properties. So we want to look at the ergodic averages, and we will try to find some good quantitative estimates on the speed of convergence for the ergodic averages. And I also want to talk about, at least a bit about a temporal distributional limit theorem that was proved recently. So in dynamics, it's common to also try to study the distributional limit theorem that arise. So you look at the ergodic integrals and you treat them as random variables. Usually what is done, you pick the initial point randomly and you want to try to center and normalize the ergodic integrals and try to prove, to see if this sequence of random variables has a limiting distribution. And something that has been investigated more recently is try to do the same thing, but instead of picking the initial point randomly, you pick the initial point deterministically, and then you randomize the time. And so you in a large window, you take your time randomly, and you want to see if the ergodic integrals converge in distribution to something. And this is a recent and I think very interesting direction. So I want to say something about this as well. Okay, so let us start by looking at the ergodic averages. So once again, setting. So I want to take quotients of SL2R, and from now on, I will always assume that the quotient is compact. So last lecture, we saw the quotient of SL2R mod SL2C. That is not a compact. It's finite volume, but it's not compact. So I will not talk about those, but I want to take quotients that are compact. The R measure, I will denote it by vol, in volume. And so the R measure was defined up to scalar. So I will now make the normalization so that the measure of the quotient is 1 to turn it into a probability space. And as I was mentioning, the Horocycle flow is the homogeneous flow generated by this specific element in the algebra. And I will call it HT, H for Horocycle, instead of pi UT. And another flow that will be useful for us is the geodesic flow, as Raymond was talking about, and is generated by this diagonal element in the algebra, and corresponds to multiplication on the right by this diagonal matrix, as we saw in the last slide. Okay, so this is my setting, compact quotient, and this is the flow that we want to study the ergodic properties with respect to this measure. Okay, so what we want to do, we want to fix, say, a continuous function and I want to study the ergodic averages. And I will denote by A for average associated to the function f at the initial point P up to time t. What can we say about this? Okay, it's a classical result of Furstenberg that in this setting, so when the quotient is compact, then the horocycle flow is uniquely ergodic. So we saw the definition in John's lecture. This means that the ergodic averages, AF of PT, when t tends to infinity, converge to the expected value of your function, so the integral. And the convergence is uniform in the initial point. Okay, I will not prove this because I think John will do it in his course. So I will cheat and refer to his lectures for the proof of this fact. But so what I want to do is very well, okay, we know that the convergence of the ergodic average to the expected value is uniform in P. Maybe we can say something about how fast this convergence is happening, and this is very important in applications. So can we do this? And this is the goal of today's lecture. And now comes one of the key observations, that is a commutation relation, commutation in quotes, relation between horocycle and geodesic flow. So I'll start by just doing a matrix computation. So if I take this matrix and I multiply by this diagonal matrix, I get this matrix here in the middle, and I notice that I can rewrite this matrix as the same diagonal matrix. There is a typo here, so forget about this. What you have to see, what you have to look at is, so here instead of r, there should be e to the minus the r. Sorry, copy and paste. So what does looking at the correct commutation relation, what does this mean? So recall that these flows are obtained by multiplication on the right. So now imagine that there is a point P in here. If I take a point P, I multiply by this metric, so it means I'm applying the horocycle flow for time r. And then I multiply by this metric. So this means that I'm composing with the geodesic flow for time t. This is the same thing, equality, as the point P is still here. So I take the point P, I compose with the geodesic flow for the same time t. And now this metric is wrong. Here there should be a e to the minus tr. So this corresponds to composing with the horocycle flow for times e to the minus tr. So the two, and this holds for any point because this is just a matrix product. So what is telling me is that this flow do not commute, but well, there is a picture in the next slide. So the orbits close up, although the length in the horocycle direction is being shrinked. So the larger t gets, the shorter this length becomes. So the same computation as in, so the same fact, apart from being computed by this matrix computation, you could have, for example, look at what happens if I do the differential of the time t map at the generator of the horocycle flow. Well, we know how to compute this, is the adjoint, and if you do the computation, you get e to the minus t u. So this means that this flow on the tangent vector of this guy shrinks it by a factor of e to the minus t. This is the same computation, and equivalently, if I look at the infinitesimal version of this is saying, if I look at the Lie derivative, so how infinitesimally the geodesic is acting on the horocycle vector field, well, this is adding a minus component in its direction. So if you so this equation is the differential version of this. From here to here you differentiate, and from here to here you integrate. Geometrically, this is what happens. So you take a point P, and you can either flow in the horocycle direction for time r, and then flow in the geodesic direction for time t, or you can first flow in the geodesic direction for time t, and then flow in the horocycle direction, but for a much shorter times, for time e to the minus t r, if t is positive. So this is a schematic picture, but this is more or less what happens in the hyperbolic plane. So these geodesics converge exponentially fast, and these horocycles are the stable manifold, so the set of vectors that would image in the future converge exponentially fast. And what this is telling you is that you have a uniform exponential contraction when you push with the geodesic. Is this clear? Okay, so why is this important for us? Okay, recall that we wanted to look at the ergodic averages of the horocycle flow. And now I take the time to be an exponential time. So I look at the ergodic averages up to time e to the t. All right, so I have my commutation relation, so I can take this part here, so HR of P, and insert the geodesic flow at times minus t composed with the geodesic flow at time t. I'm not doing anything so far, but now I want to commute these two. So I use my commutation relation, and I can take this phi to the minus t on the left. Here I have phi to the minus t, and then here I have the horocycle flow at times r e to the minus t at the point phi t of x. I just use the commutation relation. So what is this telling me? If now I take this and I plug it back into this formula here, okay, so I have my ergodic averages, and instead of HR of P, I plug this formula in here. So I have this formula here, and now I do a change of variable. This r to the e, r times e to the minus t, I will call it r prime. I do a change of variable. This factor here gets eaten in the change of variable formula. And so if r was going from 0 to e to the t, and now I change variable, so now my integral goes just from 0 to 1 of f composed with phi x to the minus t of hr at the point phi xt of p. So what have I done? I've taken my horocycle average over a very long horocycle orbit, and I'm repeating is as a very short horocycle orbit. So now this is an integral along a horocycle orbit of length just 1. But in order to do that, I had to change my function. Before my function was f, now my function is f composed with phi x to the minus t. And I changed also the point. Now my point is phi xt of p. Okay, this is what people, this is a very simple instance of what people call renormalization. You take a very long orbit of your flow, and by some other dynamics, you manage to map it down to a very short orbit. But in order to do that, you change your function and your point. Okay, so these are my ergodic averages. So I will call the function j. So the function j is going to be the integral from 0 to 1 of the function f composed with phi x to the minus t, integrated along the horocycle orbit at time t. This is a definition, and with this definition, I can rewrite my ergodic average up to times e to the t in terms of this function jf. So if I want to, what we proved is that if instead of studying the ergodic averages of the function f at the point t for time t, I can look at this function jf. And the point is that this function is much nicer for what I want to do. So if I understand something about this function, then I can understand something about the ergodic averages just by substituting the point with the image under the geodesic flow for time log t. Recall here was an exponential time, so if here I put t, here I have to take logarithm. And so here the average was going up to t, if it's up to e to the t, if I want to go up to t, I have to put a log. So all of this is to say that instead of studying the ergodic averages for the horocycle flow, I will study this function j, and once I know something about this function j, I can recover whatever I want about the ergodic averages for the horocycle flow. Okay. Let us take now not just a continuous function, but I want it twice differentiable. So if it's twice differentiable, if I apply the Casimir operator that we just defined, I get a continuous function. So recall that the Casimir operator was the second derivative in the r directions minus second derivative in the geodesic direction minus second derivative in the y direction. Okay, so now I fix my initial point, and I want to study my function j, where now I think the function to be fixed, I want a C2 function, and the point t to be fixed. So I see it just as a function of t, just as a function of time. And here comes the key idea. So assume that your function was not just a C2 function, but was also an eigenfunction of the Casimir operator. So assume that I give you a C2 function such that, well, it would be C infinity, such that when you apply the Casimir operator, you obtain a multiple of itself. And I haven't said it, but these operators turns out to be self-adjoint, so the eigenvalues are going to be real for sure. Imagine that I give you a function. Remember, if my function f was invariant by R, the Casimir was exactly the hyperbolic Laplacian. So if you don't like to think about the Casimir operator, take an eigenfunction of the Laplacian on your compact surface. This would be a function that satisfies this assumption. So take a compact surface, you have the hyperbolic Laplacian, it has infinitely many eigenfunctions that are smooth functions. So they satisfy this assumption where the eigenvalue is going to be positive. And the key proposition tells you, okay, for functions of this type, my function j satisfies the ordinary differential equation. So my function j satisfies that if I take its second derivative plus its first derivative plus mu being the eigenvalue, times the function j itself, this is going to be equal to e to the minus t times something. Something that will depends on p and will depends on t. Do not spend too much time looking at what it is now. But what is saying is that my function j as a function of time satisfy. So on the left-hand side, I have a very nice linear constant coefficient second order ODE equal to e to the minus t something. Okay, here I have to say something about the something in the bracket. This is a derivative of your function along some other direction, the unstable Horocycle direction. Let me prove this proposition. If there are questions, please stop me, but I will prove this proposition. And the proposition is not very hard to prove. Okay, so for the computation that I want to do, I don't really like this basis. So I want to express my Casimir operator in terms of the basis u, x, and v. So how do I do that? I know what the Casimir is with respect to this basis, so I can rewrite R and Y in terms of V and U. So R is 1/2 V minus U, and Y is 1/2 U plus V. If I do this, okay, instead of R, I put 1/2 V minus U, 1/2 V minus U. Instead of Y, I put V plus U, V plus U. So if I expand the bracket, I obtain this expression here. This expression would be exactly the Casimir with respect to this basis. And now I do one more algebraic operation, namely, instead of VU, I will write, instead of VU, I'll write UV plus its commutator. And the commutators turns out to be twice X. These are computations with matrices that you can carry out. So if I now, instead of VU, I plug this one over here, I obtain this formula here for the Casimir operator. Okay, let us put this on the side for a moment. And let us make another observation. So remember that in the integral that defines the function j, there was f composed with phi x to the minus t. What happens if I differentiate this with respect to t? Well, by definition, I get the derivative of f along the geodesic direction with a minus because here I'm taking negative times. So the derivative of f composed with f phi x minus t is minus xf. So this is the derivative in the geodesic direction composed with the point I'm at. Similarly, if I do the second derivative, I get, so I get minus minus, so I get the minus cancels, and I just get the second derivative x squared of f composed with the flow. Okay, so this was my function j, and this is the new expression for the Casimir operator that I found. So let me compute what would be j if instead of f there was the Casimir operator of f. Well, I get x squared plus x, but I can rewrite, since x squared is the derivative of f composed with this, I just get minus the second derivative of j. And since x is minus the derivative with respect to time of this guy, this I get minus the first derivative of j with respect to time, minus this part over here that I leave it as it is. Okay, this is what happens if for j instead of f there was the Casimir of f. But now I use my assumption. My assumption was that Casimir of f was equal to mu times f. So this term over here is going to be mu times j. Does that make sense? So I get mu times j equal to minus j second derivative, minus j prime, plus this guy over here. Okay, this is what I will written here. And we're almost there. Why? Okay, what do I have on the right-hand side? On the right-hand side, I have the integral of a new function, the new function being u, v, f, u being the stable horocycle, v being the unstable horocycle, and f being the function, composed with phi x minus t, composed with hr. Okay. But how did we get from here? We did, to get to here, to this integral from 0 to 1, we did a change of variable, and we started from the horocycle averages. So I'll do the same thing backward. So I'll go backward and recommute this on the other side. So this term here, if I use the same commutation I used in one direction, I use it backward to go back. So what do I get? Okay, I recommute these two, so I get minus the same integral. Here I get the horocycle flow at time e to the t r composed with the same object over here. And now I do the same change of variable in the opposite direction. So I get the average minus the average, so 1 over e to the t times the integral from 0 to e to the t of the horocycle, the ergodic average for the horocycle flow of this function uvf at the point phi x minus t of p. And now why have I done this? Because now I have an ergodic average of along an horocycle orbit of a function that is a derivative in the direction of the horocycle flow. So this u here is the derivative in the direction of the horocycle flow. So I'm integrating a derivative. So I use the fundamental theorem of calculus to say that this integral here is the value of the function in the function vf at the extrema, like the difference of the value of the function at the extrema. So I get minus L the t times this difference, that if you write it down is this object over here. And this proves the proposition. So it was a computation, but it was, I mean, this is a, I think, it tells us a lot about the function j now, as you will see. So what have we found? We found that our function j that we want to understand because it relates to the ergodic averages satisfies this second order ODE linear with constant coefficients. So j double prime plus j prime plus mu times j equal to e to the minus t times some function gt. Gt was this expression over here. I mean, here I written the dependence only on the time, but it actually depends on the function and on the initial point, but I think of them as fixed. But all I care is that this function gt satisfies some uniform bounds in t. Why? Well, So if I want to take the maximum of this guy, well, this as a function of t, well, this is the value of these derivatives of f at the point that moves. But if I just interested in upper bounds, for any point p and for any time t, this function g will definitely be bounded by twice the subnorm of the derivative vf, which in turn is bounded by twice the C1 norm of f. So what I found is that this ODE, okay, is non-homogeneous because I have a non-zero here on the right-hand side. But on the right-hand side, I have something that is e to the minus t times something uniformly bounded in t. So it's not this equals 0, but is this equal something of order e to the minus t. And well, at the point, maybe we don't really remember how to solve these equations, but if you go back to a textbook, maybe to some long forgotten course in linear differential equation, you find out that this equation is solvable. You can solve it exactly. So to solve it exactly, well, you have to look at the associated characteristic polynomial. So the polynomial obtained by taking this guy x squared, this guy x, and this mu. So you look at this polynomial, this second degree polynomial, it has two roots that are 1 plus or minus, basically the 1 minus 4 times mu, the square root of 1 minus 4 mu. So I will call mu to be precisely this guy here. So the unique, either positive, real, or purely imaginary with the positive imaginary part. So that basically mu is the square root of 1 minus 4 mu, but square root chosen either positive or purely imaginary with positive imaginary part. And the solutions to this equation, well, it involves a summing of two terms whose behavior is dictated precisely by this number over here. So again, maybe we look in a book or we ask what from alpha, we solved it. And so the solution is a bit, if you want to write it down precisely, well, it depends on what these roots are. They can be real or they can be with the real part 1/2 and then purely imaginary. And maybe you want to do, there is also the case where mu is equal 1/4 that you have a double root. So these cases have to be treated slightly differently because when you have a double root, there is an extra linear factor appearing. So just to give an example, let me assume that our mu was in between 0 and 1/4 strictly. So that 1 minus for mu is positive, so that mu, when I take the square root, is some number in between 0 and 1, strictly including between 0 and 1. I can write exactly what is the solution. I can find an expression for j of t. And this is the term that basically will dictate how j decays. So it's e to the minus the root of my characteristic polynomial times t. So here I have two roots, one with the plus and one with the minus. So I have two terms, e to the minus 1 of the root times t. And here I have the other terms minus the other root times t. And then some term in bracket, where in bracket I have this integral from 0 to t of this function here that involves the non-homogeneous part of my equation, and some constant that depends on the initial condition, because I mean, you have to, once you fix the initial condition, j0 and j prime of 0, that determines the two constant that appears in this bracket. Okay. I want to do one more manipulation to this equation, namely, I would be even happier if inside these brackets there was really a constant, not just because inside the bracket this term depends also on t. But I'm happy even with some extra error terms as long as here I have some nice constant, So if you notice, so here I have the integral from 0 to t. If there was the integral from 0 to infinity, I would be happier because then the term in bracket would be a constant. So what happens if instead of this integral from 0 to t, I replace with the integral from 0 to infinity? Well, I commit an error, the error being the integral from t to infinity, bounded by the absolute value of the integral from t to infinity, which is multiplied by this term in front over here. So by replacing this integral with the integral from 0 to infinity, I commit an error once I multiply also by the factor in front of the parenthesis that is bounded by some constant that depend on my value nu times the C1 norm of f. Recall that this G was bounded by the C1 norm of f, twice the C1 norm of f, times e to the minus t. Because if you see, well, this is bounded by a constant. So once you integrate e to the minus this factor and you multiply by e to the this factor, this minus plus nu cancels with this one, and you're left with minus 1/2, that is minus 1, e to the minus t. So what I can do is, okay, I will give a name to what I find in the brackets once I replace from the integral from 0 to infinity, from 0 to t with the integral from 0 to infinity. And I will add an error, which is of size e to the minus t. And okay, maybe this is a bit scary, but what I'm doing here is just I'm giving a name to the term that was appearing in brackets, and I will call it d. Okay, it was dependent. I had two terms, so one with the sign plus, one with the sign minus. So I have d plus and minus. It was depending on the function f. So here I'm re-expliciting all the dependencies. So it was depending on the function f. It was depending on the eigenvalue mu, and it was depending on the initial point. But it's a constant in time. So this is a constant. And I have some uniform bound that was coming from the bounds that I had of my function. So it's something that is bounded by a constant that depends on mu and on the C1 norm of f. And so finally, I've rewritten my function jt. I found a very nice expression for my function jt as e to the minus some constant times t times my d plus f plus another term which has exponential decay times a constant times a little times an error plus an error that is of size e to the minus t. And this is for my j. So now that I have information for j, I retranslate it back to some information for my ergodic averages. And so what have we proved? We proved a very interesting result. Well, let me call it pt, the image of p under the geodesic flow for time log t. What did we prove? We proved that if we take a C2 function that is well, it would be a C infinity function, that is an eigenfunction of the Casimir operator, say with some eigenvalue between 0 and 1/4, but you can do it for all eigenvalues. Then there exist two bounded functions, d plus and minus mu of f, that are uniformly bounded by some constant depending on mu times the C1 norm of f, such that my ergodic averages, so recall that once I want to go from j, I've written it here, once I want to go from j to the ergodic averages, so here the ergodic averages was an exponential time and it was giving me j at times t. So if I want to find the ergodic averages at time t, I have to calculate j at log t. This was so the result is that if I look at the ergodic averages of f, I can write them as a sum of two terms that have a power decay. They have a polynomial decay where so t to the minus something, and the something is related to the eigenvalue of the Casimir. So two terms by two explicit decay. The value of the constant in front is the value of some explicit function evaluated at the point t followed by time log t under the geodesic, plus an error term that is of size t to the minus 1. And again, the proof is just take the information we just found for j and translate it back to the information for the ergodic averages. Does that make sense? So if you want, you can specialize this for eigenfunctions of the hyperbolic Laplacian. So this tells you how the ergodic averages for our cycle flow for eigenfunctions of the hyperbolic Laplacian behave. Yes?
This bounded function is depend on the eigenfunction and the eigenvalue.
Yes.
Only depend on this.
Yes. Yeah. So in particular, we also find that for this function, well, this function turned out to have zero integral. And we also proved that in particular, the ergodic averages go to zero, which thank goodness that's the case. So, okay, now you might ask me, I want to know about generic function, not just these very special ones. If you want to know. Yes.
So you said mu in this case is between 0 and 1.
Yes.
So the first term is really this t to the minus 1 plus.
This is the largest. They have a different.
Right.
Right. So they are both between 0 and 1.
But one is dominant.
One is this is the right. This is the dominant. This is the second one, and then you have the error of size t to the minus 1. Yeah.
Is there a more deep reason that you choose the upper bound as the quarter?
No, just because at the quarter, the ODE that we found before is the double root. So the expression here would be t to the minus 1/2 times this guy, t to the minus 1/2 log t times this guy, plus. So it's just that you have to write it differently, but you can solve it. This is just an example of. Once you have the ODE, you can solve it in all cases. If t is larger than 1/4, you have two terms in here that have the same decay t to the minus 1/2, but they also have a rotation component. So one could be something like sine of log t, and the other one would be cosine of log t. Two terms that have in absolute value the same decay, but okay. So what happens for a general function? I will not prove it, but this is the key ingredient to prove this result. That is, okay, so as far as I know, I think the first proof was given by a seminal work by Flamini and Forni in 2003, and then generalized by, well, strengthened in some other directions by Buffetto and Forni. But the proof I presented to you is by myself. So what you can prove in general, you can prove that there exists some constant that depends only on the space you are in, such that the following holds. So every time you have some function and you need it to be sufficiently regular, so here I'm being a bit brutal and taking a C4 function. Okay, fix one of them. So now you look at the whole spectrum of the Casimir operator, and the spectrum of the Casimir operator which is positive, coincides with the spectrum of the hyperbolic Laplacian. So you have a sequence of eigenvalues diverging to infinity. So for any such mu, so you have a sequence of eigenvalues diverging to infinity, you can find two bounded functions. These are precisely the bounded functions I showed you before. And the sum of their sup norm will be bounded by this constant times the C4 norm of f, such that for all initial points and all times, the ergodic averages are, well, the ergodic averages converge to the expected value, and then you have a full expansion, and here comes also the other eigenvalue that I did before. So you have a sum over all eigenvalues of terms that decay. So for each eigenvalue, you have two terms, as we had before, that have a power decay times the constant being the value of this function at the point t pushed with the geodesic forward time of t. The eigenvalue 1/4 is a bit special because you have a double root. So in that case, the two terms are t to the minus 1/2 and t to the minus 1/2 times log t. And then an error term that is of size log t over t. And this is the result in full generality of what you can say about the ergodic averages for Horocycle flow on compact spaces. Okay, I will not prove this. I will just tell you how you can, what you have to do to go from what we proved in all details now to get to this one. But it would be a recipe, like it, not giving, just what you would have to do. What would you have to do? So the proof uses the following ingredients. So you take any L2 function, and what turns out to be from some general results on representation theory is that you can write it as a sum of function f mu, where mu is parameterized by the eigenvalues of the Casimir operator, where all these functions are in L2 and they are eigenfunctions for the Casimir operator. So you see where we are going. You take any L2 function, we can split it into an infinite sum of eigenfunctions of the Casimir operator. So we want to apply what we proved for eigenfunctions of the Casimir operator. Okay, what's the problem? This is true in L2. And our assumptions was that these eigenfunctions was a C2 function. Okay, this is not a big problem. If I ask for some more regularity of the function, I can make sure that these functions are in C2. So for those of you who know, if you ask that this function is in some Sobolev space, then you can make sure that these functions are in the same Sobolev space. So if you can use some Sobolev embedding theorem to say that if this is in a Sobolev space of sufficiently higher order, then the functions that appear here will be in the same Sobolev space, and that Sobolev space will be embedded in C2. So you can make sure that these guys are in C2. And finally, to conclude, well, this spectrum here, the eigenvalues of the Casimir are quote-unquote explicit. What do I mean by this? I mean that the positive part are the eigenvalue of the Laplacian. So whatever you know about the eigenvalue of the Laplacian will be the same for the eigenvalue of the Casimir. But what is important is that you have 0 that is isolated, and then you have an increasing, non-decreasing sequence of eigenvalues divergent to infinity. And the negative eigenvalues, those are really explicit. You can write them down what they are. And so in particular, you can find a corollary that maybe is what you care, and this was proved, it was proved earlier than Flamini and Forni or Buffet and Forni by Burger in the 90s, in 1990. And in particular, since 0 is an isolated eigenvalue, well, in all the sum we found in the previous slide, the first term is the one that gives you the leading error. So if you're just interested in estimating from above the error you commit on the ergodic averages to the expected value, well, this will be bounded by some constant, depending only on the quotient, the C4 norm of F, times the negative power of T, where this nu 0 is the nu associated to the smallest positive eigenvalue. Does that make sense? Okay. So we found some very precise quantitative information on the ergodic averages for Horocycle flow. I will conclude by, okay, I will not go into proof, say something more about these functions over here. So I just told you these are bounded functions. You can actually be a bit more precise and prove that they are actually Hölder continuous. So this is maybe something that you need in some other application. So by looking, because remember we found some explicit expressions for these functions here. And explicit, okay, maybe you cannot, you can try to extract as much information as you can for the expression you have. So in particular, you can find out that these are Hölder continuous. So the function d plus associated to the eigenvalue mu is Hölder continuous with the exponent 1 minus the real part of mu over 2. And the one with the minus as Hölder exponent 1 plus the real part of mu over 2. And again, there are some nuisances at 1/4, and indeed, d plus 1/4 is as Hölder exponent 1/2 minus epsilon for a positive epsilon. So this is just a nuisance. And the proof, again, I will not go through it. It's here on the slides that I will upload at some point, like today or tomorrow. It's just by direct inspection of the expression that we found before, and I'll skip it. But it's an exercise. And okay, maybe I'll stop here because my time is up. And yeah. Simon will talk about this before.
Are there any questions or any?
Quickly explain that you say the new intersect with the positive real numbers that is corresponding to the hyperbolic Laplacian. I didn't follow that.
Yes, so you can look at the eigenvalue of the Casimir, the eigenvalues of the Casimir operator, and so they are all real because it turns out to be a self-adjoint operator, so it has real eigenvalues. And so 0 is an eigenvalue. There are constant functions, for example, but there are other functions that have eigenvalue 0, and this actually will be relevant for this part of the talk. And then you have positive eigenvalues, and the positive eigenvalues are precisely the eigenvalues of the hyperbolic Laplacian. And then you also have negative eigenvalues that are explicit.
If you say so, the quarter is really means something. 0 to quarter is the discrete spectrum of the hyperbolic Laplacian, and we're bigger than one quarter. When you're bigger than the quarters infinity, the continuous spectrum of
I'm in the compact case.
you only consider.
Only compact case, so I don't have continuous spectrum.
So yeah, so that's what I'm trying to say. So this one quarter is not that you pick one.
No, I didn't pick it. I hope I didn't say this. No, it's. I mean, in our case, it turned out by the analysis, but it has an important meaning. Yeah.
Are there any more questions?
Yeah, I wanted to ask. So can you maybe explain again what's the difference between what you got and what Berger got? So why does he have an explicit exponent and have a slog?
No, what I'm saying is that Berger found an upper bound, which is the same upper bound that you get from here. If of this sum, you take only the first term.
Okay. So this is more precise.
This is much more precise, yes. But indeed, this result is 40 years ago. So, no, 30. But the method I presented, I think, is also inspired by this work. So, yeah, so this is a full expansion, but if I wrote it as a corollary, so in the slides I wrote corollary, because what I mean is that if you take all this infinite sum and you just take look at the first term and then you throw everything else in the error, you get the upper bound that Berger got. Yes.
Are there any more questions?
Is there any similar result?
When it's non-compact, you have problems. One problem being that the Horocycle flow is not uniquely ergodic because you have closed orbits. And in particular, you can imagine, so those closed orbits will never equidistribute if you start from one obvious point. And you can imagine that if you can have orbits that spend an incredibly long time close to these closed orbits. So you can imagine to have orbits that will equidistribute, but very slowly. So you don't hope to have some bound that will also uniformly on the point, but you can have statements of the form if my point is Diophantine in actually the sense that Reinhold was saying, then you have some at least some upper bounds on the ergodic averages, and the results in this direction, as far as I know, were investigated by Strömbergsson. So Strömbergsson has results precisely of this form. So in a finite volume non-compact quotient, if your point satisfies some Diophantine condition, then the ergodic averages can be bounded by something. But in non-compact case, you cannot really hope to have uniform bounds. It will depend sensitively on the point you consider.
Okay, let's thank the speaker again.